As we dive into analysis, we're going to focus on streams and watersheds. A watershed is an area on the earth where all the water flows through, all the water that falls into the watershed will flow through a single exit point. The exit point is also known as a pour point. This is a great way to divide up land from a natural system and therefore a natural resource management way as well. Because usually the things within the watershed are more connected than things in the next watershed. We'll talk more about that. Streams, rivers, creeks, lakes all drain a watershed. And while not all the water really flows out through the same exit point, it can be diverted. That's mostly the case. Also, streams are important ecosystems for habitat, wide variety of different organisms, and really drive a lot of the way the systems work. Okay, so again, a watershed is where all the water that falls into the watershed flows through the same location, exit location, or pour point out here. Yeah, I like this graphic a lot. So if water falls over here, it's going to flow out a different watershed. Same thing over here, but anything that falls in here. Again, it's not totally true. We could have a dam that diverted water outside the watershed. Some of the water is going to go into aquifers. It may take a while to drain, but eventually it will actually drain out the same watershed. You could have springs flowing across the watershed, but mostly the water that flows in the watershed is going to flow out the same point. These are watersheds defined by the National Hydrology data set. Notice that they aren't exactly the way we talked about watersheds, like all of California is one watershed. In reality, there's a whole bunch of watersheds in California. This is the Klamath one. The Sacramento River is the biggest one. It's huge. There's quite a few, but they've grouped them together. Okay. Now, a better term for those is hydrologic units. In other words, those are hydrologic units that the federal government has divided up the country into for management purposes. With those come hydrologic unit codes. So a number is associated with each of these. Now, these are really big ones. We're in 18 in California, 17, 10. I mean, these are huge, right? So this works at a very large extent. I notice that there's two numbers here. You can then divide up the country more, and in fact, there's 4-digit HUCs, and then here I'm showing the 6-digit HUCs, and you can see that California now has Klamath as one watershed. Sacramento Valley is several still. It's broken up into several because it's huge. San Bernardino is pretty much one. Okay, LA Basin there is one. So we're getting more detail, and this is one of the things is the nature of a watershed is you can break them up into finer and finer detail, again, for management. Okay, stream networks are how we refer to the flow of water coming out of a watershed. It's also referred to as rivers and creeks. In reality, everything that has water in it that is moving or stagnant is going to be part of a stream network. So that includes lakes and swamps and everything. We put them all together and show water flowing through the network. And you'll see that this week. These provide drainage for the watershed, for the water to flow out. It also divides up the watershed by dividing up the stream into segments. Now those segments are called reaches. It's another name for it. And sometimes the segments in a GIS correspond directly to reaches, sometimes not, because the reaches are technically the connections or the area of a stream, okay, from a confluence to another confluence. Stream networks also have a direction of flow. Water flows typically in one direction, and a good stream data set should connect all the reaches together to an exit location, and typically just one. So here's another diagram showing a stream. Here we've got a confluence. That's where multiple reaches come together, and then you have a reach again flowing downstream, eventually coming to a pour point. So reaches, direction of flow, confluence, and pour point are all important terms, as well as stream network. Okay, we take a look at Google Maps and ask what's wrong with this picture. Okay, we're going to be looking at Arcata Community Forest, which is a fascinating place to study and do GIS work with. Take a look at the streams that are shown on Google Map. there's a little bit of a problem, like right here. Okay, this is showing the streams that are visible above ground. Well, the problem with that is I think that's where the lake is. Over here, I think this is where the stream goes underwater or underground. And it does the same thing here. This is where it goes underground into a pipe. So we're not really seeing the stream network. We're seeing the stream that's visible above ground. So this works for some things, but not for analysis of stream networks. Here's the data from Arcata Forest streams. From the city of Arcata. Again, it's got some problems, and you'll see this with a lot of these stream network data sets. LiDAR can make this better. LiDAR is much higher resolution. Most of our dams in the country are 30 meters. We can also get 10 meter now, so a lot of the hydrology data is being redone at 10 meters. LiDAR can get much more accurate, but still not perfect, right? We've still got some issues that are going to cause problems for us in analysis. This is the National Hydrology Data Set. We'll take a look at its data as well. It's a very complex data set with a lot of great information. It includes flow and a lot of other information, lakes, etc. Okay, so we're going to create our own stream networks. You're going to take a look at a number of the existing ones, and then you're going to create your own. This begins with a quote-unquote good dam. The 30-meter dams were pretty good quality. We got the 10-meter dams, and they're actually better resolution, yet have more quality issues, which is interesting. We'll fill sinks because there can be single pixel little points that are way off. Then we find the flow direction, we accumulate the pixels downstream, threshold the accumulation, and then convert the streams to a polyline. Really, I should say a polyline network. Okay, so as we go through this process, you're going to want to ask, is the dam high enough resolution? Is a 10-meter dam good enough? If you're working across a large area, 10 meter is more than enough. If you're working a very small area, you're trying to find very small streams, especially at headwaters or tributaries, it may not be good enough. You may need LiDAR, and LiDAR is becoming more and more available. That's giving us 1 meter, which allows us to find really tiny streams. It's awesome stuff. And we can see a lot of other issues with water and LiDAR. Then we fill the sinks, and you may have to remove artifacts, and we'll talk more about that in lab. Basically, we may have to clean up the dams. And then you really want to minimize the processing. In other words, you want to use the dam as close to its original state as possible, because any processing you do is going to introduce artifacts that could cause problems with finding the stream network. Now, if you do processing, don't use nearest neighbor. Okay, usually we'll say use nearest neighbor because it maintains the original data. This is for resampling. However, we want to actually smooth it in this case because we want the water to move downhill. Water moves better over smooth surfaces than it does over bumpy ones. So when you're reprojecting or any type of processing that's going to resample the data, don't use nearest neighbor, use bilinear or a convolution if available, cubic in ArcGIS. Okay, filling sinks. So most dams include zero values. Supposedly these are where the sensors have dust on them, and so all of a sudden you get a zero in the middle of nowhere. Need to be filled. Now, the software you'll be using that I've written in Blue Spray will deal with the sinks, so it's not critical anymore, but it is a standard part of the process. Now, take a look at this dam, and hill shading is a great way to find artifacts, because if you do hill shade of this dam, you might wonder, are those horizontal lines actually on the land? Probably not. This is not a terraced area, okay? So those are a problem, and that happened in the processing, either because they use nearest neighbor, or depending upon the extent of the processing, those can happen without nearest neighbor. Even with bilinear smoothing, you can still get those types of terraces, and that's a problem because water will flow across the dam, but it'll follow those lines, those artifacts, and it'll completely screw up your data. Trust me, someone in lab will use this, and we'll get to see that because it's kind of cool to see. It's not desired, but it's kind of cool. So again, minimize your processing and resample with interpolation to avoid this, okay? Now also you can do smoothing to make some of this go away as well. If someone gives you a dam that's already messed up, you can use smoothing to help get rid of this. Okay, as we go through this process, you're going to see a number of different types of rasters. You're going to be doing this in Blue Spray because it's the only software that does this. One is you're going to see a direction raster, and it actually points downstream. And you can see here where you can see the water uphill over here is flowing down and then flowing down and then flowing into a small stream, which flows into a bigger stream, which flows into a bigger stream. So the arrows are pointing the direction. Now take a look at that little zero there. That is a sink. Now that's not a big sink. Okay, that could be a lake or something. It's just something that in the dam happened to be below all the pixels around it, or have a lower value of all the pixels around it. So the water is going to flow right into that sink, and we can fix that, but we have to take a special step to do that. Okay, after we find the directions, we then run an accumulation raster, which accumulates all those pixels downstream into our pour point. And that's what you're seeing here, is you're seeing the number of pixels that have been accumulated into each pixel. And that's why it's very light up here at the headwaters, very dark, close to zero. And down here it's brighter, higher number. And you can get very high values very quickly. So this is scaled to help you see the lighter, they look light to me because they're close to the background color, black. Okay, and this counts the pixels that drain through each pixel. So in other words, the value of each pixel will now be the number of pixels that are upstream or that it drains. That's an accumulation raster. If we threshold that, in other words, just convert all the pixels that are above a certain value to 1, leave the others as 0, now we can see our stream network more easily. Of course, we've lost the accumulation, which you might want, but this makes it more visible, and that allows us to create a polyline, which now creates our stream network. We have our very nice stream network now. Actually, this is one from ArcGIS, I can tell, because that's an artifact that it does. Okay, so here's Arcata Forest, and we've got our stream network. All right, now, a stream network is only a line segment that represents the lowest portion of the stream or river. Okay, so optimally, we'd really want the thalweg, which is the lowest elevation. Okay, and we're not necessarily getting that because our dam may not have it in it. In fact, the dams will tend to have flat areas where there's a lake or a wide river. Okay, so it's really not getting the lowest point. We're representing that, we're saying that, but it's not necessarily the case. Okay, eventually with LiDAR or with the UAV, you can fly at low water and you can get closer to that, or you can even draw it in, and some folks have done that. Okay, so now to create the watershed, we have to create the pour points. We have to find the points along the edge of our watershed that water is going to flow out of. And we want to do that at the accumulation, the highest accumulation pixel. In other words, we find that pixel back in our accumulation raster, like maybe that's here, one of these pixels, or more clearly here, okay, and here, these would be our pour points. And Blue Spray will automatically find those, or you can specify them. You just have to make sure they are right inside that accumulation. In Arc, you can snap the pour points accumulation raster. Blue Spray will create them for you, or you can create them manually. Then you go ahead and run the Watershed tool to find the watershed, and that will work backwards from the pour points using the direction raster and the pour point layer to find the watershed. So here's our final result. We can see the watersheds for Arcata Forest. Now, I do need to mention that each of you is going to get a little bit different watershed, and you're going to get a little different watershed because you're going to pick different pour points. The selection of the pour points is really critical. You want to make sure you get all the watersheds that cover Arcata Forest, because we're missing some here maybe. And you want them to be a size that's appropriate for management, which you can pick.